Formwork is the term given to either temporary or permanent molds into which concrete or similar materials are poured. In the context of concrete construction, the falsework supports the shuttering molds. Formwork and concrete form types. Formwork comes in several types. Traditional timber formwork. The formwork is built on site out of timber and plywood or moisture-resistant particleboard. It is easy to produce but time-consuming for larger structures, and the plywood facing has a relatively short lifespan. It is still used extensively where the labor costs are lower than the costs for procuring reusable formwork. It is also the most flexible type of formwork, so even where other systems are in use, complicated sections may use it. Engineered formwork system. This formwork is built out of prefabricated modules with a metal frame and covered on the application side with material having the wanted surface structure. The two major advantages of formwork systems, compared to traditional timber formwork, are speed of construction and lower life cycle costs. Reusable plastic formwork. These interlocking and modular systems are used to build widely variable, but relatively simple, concrete structures. The panels are lightweight and very robust. They are especially suited for low-cost, mass housing schemes. Permanent insulated formwork. This formwork is assembled on site, usually out of insulating concrete forms. The formwork stays in place after the concrete has cured, and may provide advantages in terms of speed, strength, superior thermal and acoustic insulation, space to run utilities within the EPS layer, and integrated furring strip for cladding finishes. A Eurocubed COF or a Eurocubed is a structural stay-in-place formwork system to build constructions in concrete. It is composed of two filtering grids reinforced by vertical stiffeners and linked by articulated connectors that can be folded for transport. A standard panel 1.10 m x 2.70 m weighs 32.7 kilograms and can be carried by hand or by any means of machine. After coffer is placed, concrete is poured between the grids, excess water of concrete is eliminated by gravity and air is also eliminated. Coffer remains in the construction after concrete is poured and acts as reinforcement. Any type of construction can be built with coffer: individual houses, multi-story buildings including high-rise buildings, industrial, commercial or administrative buildings. Several types of civil works can be done with coffer. Coffer is delivered completely assembled from the factory. No assembly is necessary on the construction site. Stay-in-place structural formwork systems. This formwork is assembled on site, usually out of prefabricated fiber-reinforced plastic forms. These are in the shape of hollow tubes, and are usually used for columns and piers. The formwork stays in place after the concrete has cured and acts as axial and shear reinforcement, as well as serving to confine the concrete and prevent against environmental effects, such as corrosion and freeze-thaw cycles. Flexible formwork. In contrast to the rigid molds described above, flexible formwork is a system that uses lightweight, high-strength sheets of fabric to take advantage of the fluidity of concrete and create highly optimized, architecturally interesting, building forms. Using flexible formwork, it is possible to cast optimized structures that use significantly less concrete than an equivalent strength prismatic section, thereby offering the potential for significant embodied energy savings in new concrete structures. Slab formwork. History. Some of the earliest examples of concrete slabs were built by Roman engineers. Because concrete is quite strong in resisting compressive loads, but has relatively poor tensile or torsional strength, these early structures consisted of arches, vaults and domes. The most notable concrete structure from this period is the Pantheon in Rome. To mold this structure, temporary scaffolding and formwork or falsework was built in the future shape of the structure. These building techniques were not isolated to pouring concrete, but were and are widely used in masonry. Because of the complexity and the limited production capacity of the building material, concrete Euro unregistered trademark S rise as a favored building material did not occur until the invention of Portland cement and reinforced concrete. Timber beam slab formwork. Similar to the traditional method, but stringers and joists are replaced with engineered wood beams and supports are replaced with metal props. This makes this method more systematic and reusable. Traditional slab formwork. On the dawn of the arrival of concrete and slab structures, building techniques for the temporary structures were derived again from masonry and carpentry. The traditional slab formwork technique consists of supports out of lumber or young tree trunks that support rows of stringers assembled roughly 3 to 6 feet or 1 to 2 meters apart, depending on thickness of slab. Between these stringers, joists are positioned roughly 12 inches, 30 centimeters apart, upon which boards or plywood are placed. The stringers and joists are usually 4 by 4 inch or 4 by 6 inch lumber. The most common imperial plywood thickness is a 3/4 inch and the most common metric thickness is 18 millimeters. Metal beam slab formwork. Similar to the traditional method, but stringers and joists are replaced with aluminium forming systems or steel beams and supports are replaced with metal props. This also makes this method more systematic and reusable. Aluminum beams are fabricated as telescoping units, which allows them to span supports that are located at varying distances apart. Telescoping aluminium beams can be used and reused in the construction of structures of varying size. Modular slab formwork. These systems consist of prefabricated timber, steel or aluminum beams and formwork modules. Modules are often no larger than 3 to 6 feet or 1 to 2 meters in size. The beams and formwork are typically set by hand and pinned, clipped, or screwed together. The advantages of a modular system are, does not require a crane to place the formwork, speed of construction with unskilled labor, formwork modules can be removed after concrete sets, leaving only beams in place prior to achieving design strength. Table or flying form systems. These systems consist of slab formwork tables that are reused on multiple stories of a building without being dismantled. The assembled sections are either lifted per elevator or flown by crane from one story to the next. Once in position, the gaps between the tables or table and wall are filled with fillers. They vary in shape and size as well as their building material. The use of these systems can greatly reduce the time and manual labor involved in setting and striking the formwork. Their advantages are best utilized by large area and simple structures. It is also common for architects and engineers to design building around one of these systems. Structure. A table is built pretty much the same way as a beam formwork, but the single parts of this system are connected together in a way that makes them transportable. The most common sheathing is plywood, but steel and fiberglass are also in use. The joists are either made from timber, wood I-beams, aluminium or steel. The stringers are sometimes made of wood I-beams but usually from steel channels. These are fastened together to become a deck. These decks are usually rectangular but can also be other shapes. Support. All support systems have to be height adjustable to allow the formwork to be placed at the correct height and to be removed after the concrete is cured. Normally adjustable metal props similar to those used by beam slab formwork are used to support these systems. Some systems combine stringers and supports into steel or aluminum trusses. Yet other systems use metal frame shoring towers, which the decks are attached to. Another common method is to attach the formwork decks to previously cast walls or columns, thus eradicating the use of vertical props altogether. In this method, adjustable support shoes are bolted through holes or attached to cast anchors. Size. The size of these tables can vary from 70 to 1,500 square feet. There are two general approaches in this system: crane-handled. This approach consists of assembling or producing the tables with a large formwork area that can only be moved up a level by crane. Typical widths can be 15, 18 or 20 feet or 5 to 7 meters, but their width can be limited, so that it is possible to transport them assembled, without having to pay for an oversized load. The length might vary and can be up to 100 feet depending on the crane capacity. After the concrete is cured, the decks are lowered and moved with rollers or trolleys to the edge of the building. From then on, the protruding side of the table is lifted by crane while the rest of the table is rolled out of the building. After the center of gravity is outside of the building, the table is attached to another crane and flown to the next level or position. This technique is fairly common in the United States and East Asian countries. The advantages of this approach are the further reduction of manual labor time and cost per unit area of slab and a simple and systematic building technique. The disadvantages of this approach are the necessary high lifting capacity of building site cranes, additional expensive crane time, higher material costs and little flexibility. Crane fork or elevator handled. By this approach, the tables are limited in size and weight. Typical widths are between 6 to 10 feet or 2 to 3 meters, typical lengths are between 12 and 20 feet or 4 to 7 meters, though table sizes may vary in size and form. The major distinction of this approach is that the tables are lifted either with a crane transport fork or by material platform elevators attached to the side of the building. They are usually transported horizontally to the elevator or crane lifting platform single-handedly with shifting trolleys depending on their size and construction. Final positioning adjustments can be made by trolley. This technique enjoys popularity in the US, Europe and generally in high labor cost countries. The advantages of this approach in comparison to beam formwork or modular formwork is a further reduction of labor time and cost. Smaller tables are generally easier to customize around geometrically complicated buildings, or to form around columns in comparison to their large counterparts. The disadvantages of this approach are the higher material costs and increased crane time. Tunnel forms. Tunnel forms are large, room-size forms that allows walls and floors to be cast in a single pour. With multiple forms, the entire floor of a building can be done in a single pour. Tunnel forms require sufficient space exterior to the building for the entire form to be slipped out and hoisted up to the next level. A section of the walls is left uncasted to remove the forms. Typically, castings are done with a frequency of 4 days. Tunnel forms are most suited for buildings that have the same or similar cells to allow reuse of the forms within the floor and from one floor to the next, in regions which have high labor prices. Cassette formwork. See structural coffer. Flexible formwork. There is an increasing focus on sustainability in design, backed up by carbon dioxide emissions reduction targets. The low embodied energy of concrete by volume is offset by its rate of consumption, which make the manufacture of cement accountable for some 5% of global CO2 emissions. Concrete is a fluid that offers the opportunity to economically create structures of almost any geometry. We can pour concrete into a mold of almost any shape. This fluidity is seldom utilized, with concrete instead being poured into rigid molds to create high material use structures with large carbon footprints. The ubiquitous use of orthogonal molds as concrete formwork has resulted in a well-established vocabulary of prismatic forms for concrete structures, yet such rigid formwork systems must resist considerable pressures and consume significant amounts of material. Moreover, the resulting member requires more material and has a greater self-weight than one cast with a variable cross-section. Simple optimization methods may be used to design a variable cross-section member in which the flexural and shear capacity at any point along the element length reflects the requirements of the loading envelope applied to it. By replacing conventional molds with a flexible system composed primarily of low-cost fabric sheets, flexible formwork takes advantage of the fluidity of concrete to create highly optimized, architecturally interesting, building forms. Significant material savings can be achieved. The optimized section provides ultimate limit state capacity while reducing embodied carbon, thus improving the life cycle performance of the entire structure. Control of the flexibly formed beam cross-section is key to achieving low material use design. The basic assumption is that a sheet of flexible, permeable fabric is held in a system of falsework before reinforcement and concrete are added. By varying the geometry of the fabric mold with distance along the beam, the optimized shape is created. Flexible formwork therefore has the potential to facilitate the change in design and construction philosophy that will be required for a move towards a less material-intensive, more sustainable, construction industry. Its potential is further demonstrated in work by Lee. Further information can be found online. Professor Mark West, http://www Manitoba CAR The Second International Conference on Flexible Formwork, http://www.icff2012.co.uk. Usage: for removable forms, once the concrete has been poured into formwork and is set, the formwork is struck or stripped to expose the finished concrete. The time between pouring and formwork stripping depends on the job specifications, the cure required, and whether the form is supporting any weight, but is usually at least 24 hours after the pour is completed. For example, the California Department of Transportation requires the forms to be in place for 7 days after pouring, while the Washington State Department of Transportation requires the forms to stay in place for 3 days with a damp blanket on the outside. Spectacular accidents have occurred when the forms were either removed too soon or had been under-designed to carry the load imposed by the weight of the uncured concrete. Less critical and much more common are those cases in which under-designed formwork bends or breaks during the filling process. This then results in fresh concrete escaping out of the formwork in a form blowout, often in large quantities. Concrete exerts less pressure against the forms as it hardens, so forms are usually designed to withstand a number of feet per hour of pour rate to give the concrete at the bottom time to firm up. For example, wall or column forms are commonly designed for a pour rate between 4 and 8 feet per hour. The hardening is an asymptotic process, meaning that most of the final strength will be achieved after a short time, though some further hardening can occur depending on the cement type and admixtures. Wet concrete also applies hydrostatic pressure to formwork. The pressure at the bottom of the form is therefore greater than at the top. In the illustration of the column formwork to the right, the column clamps are closer together at the bottom. Note that the column is braced with steel adjustable formwork props and uses 20 mm through bolts to further support the long side of the column. Gallery. See also, Perry, MEVA Formwork Systems, Outenard, Pascal Formwork, Docker Group, Climbing Formwork, Concrete Cover, Milady, Slip Forming, Mold Release Agent for Formwork. Literature: Matthias Duck, Einsatzgebiet der Gleichschalung und der Kletterumsetzschalung, Ian Vergleich der System 2010, Verlag Diplomabieten Agenta, Hamburg, ISBN 978-3-8386-0295-0. The Concrete Society, Formwork, A Guide to Good Practice. References: Formwork, A Guide to Good Practice. External links: Stripping Time of Formwork as per India Standards, an illustrated glossary of the terms used in temporary types of construction work. Formwork, Scaffolding etc. 1. Formwork, Scaffolding and Shoring Definition and Productivity.